We'll start this segment this week off by introducing a concept which is probably the most important concept in computer science. It's the idea of graphs, arguably the most important concept. And graphs in computer science are not like graphs you saw probably in high school where you're plotting on the x-axis and y-axis two different variables and plotting the relationship. So what's a graph for computer scientists? So a graph consists of a set of vertices and a set of edges. Vertices, or think of vertices as points, and think of edges as links connecting these points. So an edge is just a pair of vertices that it's linking, and a vertex is just a single point. So of course, graphs can arise very naturally in the real world in a number of settings. For example, you could have cities on any map as the points or the vertices, and the roads connecting cities as the edges between the vertices. Another example, more current, is a communication network or the internet, where individual routers or individual end hosts are points, and the links you have connecting these end hosts and routers are the edges. In a communication network, again, it's the same sort of thing. So those are some concrete and real-world examples of graphs. But graphs can also model more abstract things, such as friendship. So for example, Facebook, which I imagine a number of you use, uses a graph where every person is a vertex, and two people are joined by an edge if they're friends on Facebook. So that's an example of the Facebook graph. The searching that we do on Google can be thought of as a slightly different kind of graph, where every web page is a vertex, and if a web page points to another one, there is an edge from the first web page to the second web page. There are other graphs that are even more abstract than that. You can actually model the similarity and lack thereof between objects by a graph. For example, if you have a number of documents in natural language processing or something, this is an important situation. You have a number of documents. You can model each document as a vertex, and you can draw an edge between two documents if they are substantially similar to each other, whatever you define your notion of similarity to be. And you don't put an edge between two vertices if those documents are not similar to each other. So because graphs can represent all these kinds of abstract relationships, practically every computational problem is first modeled as a graph, and then we ask a question about the graph. So it's important that we understand all the terminology associated with graphs, because they will be useful in solving all these problems. So again, graphs have these points called vertices. In this case, A, B, C, D, E, or the vertices. A is one vertex here. We can draw them as circles or just a point. Vertices are sometimes also called points. That's less common, but more commonly they're actually called nodes. Vertices are also called nodes. That's a term that we will use interchangeably. Vertices are connected by edges, and these are sometimes called links. Not so common. Edge is probably more common. So those are two terminologies. Now, mathematically, a graph is a finite set of vertices. The set here is the set A, B, C, D, E. So this graph G, usually graphs are denoted by the symbol G. We can write it as equal to a set of vertices V and a set of edges E. Okay. So what is V? V is just the 5 vertices in this case. In this example, it's just A, B, C, D, and E. So that's a set V. What is the set of edges? Well, the set of edges, I won't write them out here because there are too many, but for example, BE is an edge in the graph. So that's represented by a pair BE. This is an edge. So BE is an edge, BA is an edge, AD is an edge, BC is an edge, and so on. So notice that in this graph, edges don't have directions. So BE is an edge. Think of it as a two-way street or a communication link where you can send messages both directions. So these are, again, undirected graphs because no edge has a direction. So in fact, technically speaking, when we represent an edge by a pair BE within parentheses like we do, mathematically this suggests that there is an order between B and E. This is the representation in mathematics for ordered pairs. But when we talk about graph theory in computer science, graphs in computer science, when we write BE, we think of it as an unordered pair. We will have reason to study graphs where edges have directions as well, and these are called directed graphs, and I will talk about them in a little while. So some terminology associated with graphs, and again, we will use this terminology frequently, so you should get familiar with all of this. Two vertices that are joined by an edge are called adjacent. So in this picture, the vertices B and D are adjacent because there is an edge between them if you look at the picture. The vertices C and G are not adjacent because there is no edge between them. One other point I want to make, sometimes we'll have to draw graphs where edges cross each other as we've done here. But that doesn't mean there's a vertex there. So there's an edge BC and an edge AF that happen to cross in this drawing of the graph. Okay? And actually that makes that's a good time to make a larger point. It really doesn't matter how you draw the graph. The graph is an abstract object which just consists of a set of vertices and a set of edges, as I described earlier. How you draw it on paper is not what defines the graph. So that's adjacency. The next concept is the notion of the degree of a vertex. So every vertex has a certain number of edges incident on it. In this graph, the vertex F has two edges, the edge FE and the edge AF incident on it. So since it has two edges incident on F, the degree of F is 2. And if you look at B in this graph, it has 5 edges incident on it. 1, 2, 1, 2, 3, 4, and 5. So there are 5 edges incident on E, so on B, so the degree of B is 5. Now the next concept is the notion of a path in a graph. If you look at this graph again, note the red things are drawn with directions, but those are just to show you what we're talking about. There are no directions in this graph again. So the sequence of vertices B, A, D, B, E is a path. What does it mean? It means that every vertex is adjacent to the previous one in the sequence. So from B you can get to A, and from A you can get to D, and you can get back to B, and you can get to E. So basically a path is something you can walk on in a graph, a sequence of vertices that you can walk from one to the next in the graph. So that's a path. Because note that this path crosses itself because the vertex B appears twice on this path. When we want to talk about paths where no vertex appears more than once, we talk about simple paths. So in this example, BAFE is a simple path because you can get from B to A, from A to F, and from F to E, and you don't have any vertex occurring more than once. That's the definition of a simple path. And the length of a path is just the number of edges on it. It's also the number of vertices minus 1. So in this case, the length of the path BAFE is 3. Next, there's the notion of a cycle in a graph. A cycle is just a path that closes on itself, and usually we want cycles to be simple except for the fact that the first and last vertex have to be the same. So an example of a cycle here is the cycle that we've indicated here, BAFEB. So you're back to the starting vertex. So you've taken a tour around some of the vertices and come back to the starting vertex, and that's called a cycle. This cycle has length 4. Again, it's the number of edges on it, or 1 less than the number of vertices on it, which is 5. What are not cycles? We explicitly disallow the cycle that just goes on an edge and comes right back. So in an undirected graph, you could imagine calling this a cycle BAB, but that is not considered a cycle. So you cannot just have cycles of length 2 that go to some neighbor and come back. Okay? And then the other thing is we don't allow cycles to repeat vertices. We are only focusing on simple cycles. So BADBE is not a cycle for 2 reasons. One, it repeats the vertex B, and second, it doesn't close on itself. It starts at B and ends at E. So this BADBE is not a cycle, obviously. And BAB is not a cycle because we insist that cycles have length at least 3. And they don't repeat any vertex except the start and end vertex. By the way, one other notion that related to adjacency is that we say that a vertex is a neighbor of another vertex if it's adjacent to it. Just a different way of saying adjacent. The notion of connectedness is very important. It's different from adjacent. So 2 vertices are connected if there is a path between them. So we defined path earlier, so the definition of connected should be clear. It should also be clear, it's not that difficult to see that if 2 vertices are connected, they are connected by a simple path. Why is that? Let's go back to the previous slide and see. So for example, you might say that, say B and, go back to this slide actually. So we could say that B and E are connected by the path BADBE. So this long path that we're giving here is a way of connecting B with E. So BAD, BE. That's a path from B to E. So that shows that they're connected. But when such a path exists, there's also a simple path which is obtained simply by short-circuiting or removing from this path all the duplicate occurrences of any vertex and what leads up to that. So if you have B and then B occurring again in the path in this case, so if you just strike out all the things that occur between the 2 copies of B, including the second copy of B, you've got a shorter path. By repeatedly doing this, we can take any path from B to E and find a simple path from B to E. Okay, so being connected is something called an equivalence relation. I hope you've seen equivalence relations before in a previous course, but if not, basically a relation is called an equivalence relation if it's reflexive, symmetric, and transitive. So what does that mean? So a relation is something that, so we're going to talk about binary relation. A relation is just a set of pairs. In this case, it's going to be a relation on vertices, so it's going to be a set of pairs of vertices. So what are we going to say? We're going to say that 2 vertices A and B are in the relation if the A and B are connected, meaning there's a path from A to B. So that's the equivalence relation defined by connected. Why is it reflexive? Well, A and A are obviously in the connected relation. There is a path from any vertex to itself. It's just the path of length 0, which doesn't go anywhere. It starts at the vertex and ends right there. So that shows that every vertex is connected to itself. The second property you require for an equivalence relation is that it be symmetric, which means that if AB is in the relation, then so is BA. So sort of applying it to this situation, what we're saying is if A is connected to B, then B is connected to A as well. Why is that? Well, if there's a path from A to B, because the graph is undirected, that same path in the reverse direction is a path from B to A. That shows that BA is also in the relation. So if A is connected to B, then B is connected to A. Finally, the thing you require for an equivalence relation is transitivity, which means that if there are 3 vertices, U, V, and W, if there's a path from U to V and a path from V to W, then there's also a path from U to W. And that's easy to see by concatenating the paths. So there's a path from U to V, let's call it P1. There's a path from V to W, let's call it P2. Then P1 followed by P2 is also a path from U to W. Of course, this concatenated path may not be a simple path, but we've already argued that if there's any path from U to W, there's also a simple path from U to W. So either way, U and W are also in the relation. So that's why connectedness is an equivalence relation. Now, once you have an equivalence relation on a set of vertices, it partitions the vertices into what are called equivalence classes, where 2 vertices are equivalent if and only if they lie in the same class. 2 vertices are in the relation if and only if they lie in the same class. And so the equivalence classes that you get with regard to the connected relation are called the connected components of a graph. So this whole thing here is one graph. You can see that the first 3 vertices that form a triangle are all connected to each other. So they are in the same equivalence class. The remaining 3 vertices are not connected to any of the first 3, but they're all connected to each other. So they form a second equivalence class. And so this graph has two connected components. A graph with only one connected component, like this one here, is called a connected graph. That's the name given to a graph that has only one connected component, meaning you can get from any vertex to any vertex using a path in such a graph. It's called an acyclic graph if there are no cycles in it. So here's a picture of an acyclic graph. And finally, a graph is called a tree if it is connected and has no cycles. And this picture shows a tree. You can see that you can get from any vertex to any other vertex by a path, and there are no cycles. So this is a tree. What is the relation between the number of vertices and the number of edges in a graph? So by convention, we will let n denote the number of vertices and m denote the number of edges in a graph. Now, if you have an n-vertex graph, what's the minimum number of edges it could have? Well, it could have 0 edges. Basically, that would be a graph consisting of a bunch of vertices all by themselves, isolated points or isolated vertices. So on the left here, we have a graph with 5 vertices and 0 edges. At the other extreme, you could have a graph where every pair of vertices is adjacent, in which case, how many edges do you have? Well, the number of ways of choosing 2 vertices is n choose 2 in general. In this case, it's 5 choose 2. This is 5 choose 2. This is equal to 10. There are 10 edges in this graph, but in general, m can be as large as n choose 2. In a tree, a vertex of degree 1 is called a leaf. There's several facts about trees that we would want to know. These are 2 basic ones, and later we'll see other facts that are important. I've stated them as theorems. The first theorem is that every tree with at least 2 nodes has a leaf. And it's kind of intuitively clear why this is true, because if you take a tree, start from any node and start walking along the tree, along the edges of the tree, making sure never to walk back on the same edge that you just walked on. Suppose you keep on going like that. You get to a node, as long as you can find a new edge to walk on, you walk on it and keep on going. And of course, because it's a tree and there are no cycles, you will never come back to the same node in this process. You'll keep on going to new nodes, but there are only finitely many nodes. So how can you keep on going to new nodes? This process has got to stop somewhere because you run out of options. And when does that happen? That happens when you walk into a node and you find that there are no ways out. Now, what does that mean? This node has degree 1, the one edge that you walked in on, and no other edges. So it must be a leaf. So that proves that every tree has a leaf. You can actually formalize this argument that I just gave about walking along until you can't go any further, and that's at that point you have a leaf. So basically, not only does this theorem show that a tree has a leaf, but it also shows you how to find one. Simply walk along the tree until you can't walk any further, and you're at a leaf. Okay, so that's the proof that trees have leaves. Another theorem, which is a little bit trickier to prove, is that a tree on n vertices has exactly n minus 1 edges. And we prove this by induction on n, the number of vertices. Now, the base case is n equals 1 or 2, and these are pretty trivial because if n equals 1, the tree consists of just a single vertex and no edges, so that n equals 1, the number of edges equal to 0. The second base case is n equal to 2. The only tree, I mean a connected but acyclic graph, is this one. So there are 2 vertices and 1 edge, and clearly 1 is 2 minus 1. So the number of edges is 1 less than the number of vertices. So the base cases are fine. Now for induction, what you assume is that this claim is true for all trees with up to n edges, n vertices, and prove it for n plus 1 vertices. So how do we do this? So suppose you take a tree with n plus 1 vertices, this one. You know that this tree must have a leaf because we just proved this earlier. So let V be any leaf in this tree. And consider the tree you get if you remove V and the edge that V is attaching to the rest of the tree with. So you get this smaller tree. If this tree had n plus 1 vertices, now this smaller tree has n vertices. Now by the inductive hypothesis, we are assuming that any tree with n vertices has n minus 1 edges. And so this tree satisfies this theorem, therefore it has n vertices and n minus 1 edges. This other tree has one more vertex and one more edge. So it also satisfies this relationship between number of vertices and number of edges because we've added one to each side. So that doesn't change the relationship. So this is n plus 1 vertices and n edges. So this is a proof by induction that any tree on n vertices has n minus 1 edges.